Hello everyone, welcome to Lecture 10. The good news about this video is that it's actually just a review video. I'm not here about to try to teach you a bunch of new things, no. We've learned a collection of integration techniques by now. So I'm gonna give you some problems. I'm gonna give you 3 more later in this video. And I'm just gonna try to think out loud like I usually do, talk about integrals, why it would occur to me to use a certain integration technique before I begin versus some others. I just want to give you insight so that when you see a new problem, you've got kind of like a first and a second choice for things you should try. It is critical. This is a review lecture. You should not see me do these problems before you try them. Pause the video, try to do these. Even if you can't complete it, try to name the technique that you would use for these, okay? I will say that there's more than one technique sometimes. So if you don't like my way and you did it a different way and it's right, then just go with it, okay? But I'll see you in just a second after you try these examples. But I'm going to go ahead and start right now. Okay, this first one, I didn't want to complicate anything, okay? So this is just kind of like a straightforward u-sub, nothing more than that. So the denominator is the problem right now. So this is a u-substitution problem. My idea is that you could have done something like this before you walked into this class. So we're going to say u is the denominator, because that's usually a good choice when you're trying to do u-substitution. You want to get rid of a complicated denominator. This means that du is equal to dx. But this also means, and I picked this one because sometimes you have to do tricky work like this, x is also equal to u minus 10. And that's important to realize. Sometimes you forget that you can rearrange the starting u equation as well. What I like to do and what I taught in my Calculus 1 class is to change the bounds from x now. So you have like an x1 and x2 here. Change them to u. So if you plug in 0 for x, you get 10 as the new lower bound for u. And then if you plug in 5, you get 15 for the new upper bound of u. So now I don't have to back substitute when I'm done. Here I'm going to plug in my x. X is equal to u minus 10 based on this equation. Dx is du from my substitution. And x plus 10 is u. So this is the integral from 10 to 15. I have one term on the denominator, so I can divide it into each of them. U divided by u is 1 minus 10 divided by u du. I'm ready to integrate. The integral of 1 is just u. The integral of 1 over u is ln absolute value of u. And now I plug in 15 and I plug in 10, because these are already bounds with respect to u. If you plug in 15, you're going to get 15 minus 10 u 15. Notice I can drop the absolute value bars now, because 15 is definitely a positive number. Minus giant parentheses when you do this. Now you're going to plug in 10. 10 minus 10 ln of 10. And we'll simplify this as much as you can. So 15 minus 10 is 5. And then I get these 10s can be brought up based on the log rule. So I get minus ln of 15 to the 10. Here I have a double negative, so I get plus ln of 10 to the 10. And this is 5. And if I do one log minus another log, it's division. So actually what I'm going to do is I'm going to do plus ln of 10 to the 10. And you're subtracting this log, so divided by 15 to the 10. And then what is this equal to? This is just 5 plus 10. I'll just take this exponent of 10 that's on both of these and move it back to the front. ln of, and then 10 over 15 is 2/3. Is it just me, or is just doing the algebra harder than the actual integral for that one? That might be just me, but I don't know. It just seemed that way. All right, I hope you tried this one as well. So what did you think? You might have thought that this was a trigonometric integral from lectures 3 and 4, because you do see a trig function. However, there's this other function that is in a completely different family. And now if I use that word, that probably gives it away, right? This is an algebraic function, and this is a trig function. So this, what I have in mind, is to do integration by parts. So I'll say IBP. And then how do you choose which one is u? it has to be higher on this list here. Algebraic, A is the polynomial x. So I'm going to pick that for my u, and then trigonometric t, that's lower down the totem pole. So secant tangent x tangent x dx, that's going to be my dv. So if I take the derivative of this, notice it goes to 0. This is very nice. So when that happens, go ahead and just take derivatives all the way to 0, and then stop. Integral of secant tangent is secant. And now before this class, you might have been stuck. But on one of your note cards somewhere, you have the integral of secant is ln secant x plus tangent x. I want you to memorize that. The integral of secant is ln secant x plus tangent x, because it makes this problem worlds easier to know that. I hope you remembered to alternate the signs, and now we're going to multiply the two non-zero diagonals together, and that's my answer. So the answer to this, using the tabular method, remember this was called the tabular method, it's going to be x secant x, and then I have minus ln secant x plus tangent x, and then plus c, because all the other diagonals just go to 0. So that's my final answer for that. I really don't like the fact that I put dx here. I just am annoyed by that, so I'm going to erase that. OK, so hopefully that was good for you. Hopefully you at least recognize that it was an integration by parts problem. If you can recognize it right away, that's half of it, just being able to see what to do. This one is actually the same process. So this is integration by parts as well. We have two very distinct looking functions. This one is an algebraic, and this one is a logarithm. So the only difference is we're not going to pick the algebraic thing this time for u. It's going to be the log, because L here is higher on the totem pole here. So it's integration by parts. I'm going to say u is going to be ln of x. And then dv is going to be equal to x to the 3/2 dx. So derivative of this is going to be 1 over x. Notice this will not go to 0 if I keep doing the derivative, so I'm just going to stop here. Integrating this is x to the 5/2 after I add 1 to the power, and then I'm going to flip the new power. And this will be plus, and this will be minus. Here's my u times v right here. So this is going to be 2 over 5 x to the 5 over 2 ln of x. That's my first diagonal. And then here I have this row here, which if it's a row, it's a duv. So I'm going to keep this in the integral. This is going to be minus, and it's going to be minus 2 over 5 is the constant. 1 over x times x to the 5/2 is going to be x to the 3/2 dx. This, I've integrated it. So that's from 1 to 4, because that's what the bounds were here. This is from 1 to 4. So here I have 2/5 x to the 5/2 ln x, 4 to 1. 2/5. I just did this integral over here. This is 2/5 x to the 5/2. And now I get to plug in 4 to 1 to this one. So first up, I'm going to plug in 4. If you plug it into this right here, you're going to take the square root of 4, which is 2, and then take it to the 5th power, which is 32. So this will be 32 for the 4. But then I'm going to multiply by 2. So I get 64 over 5 ln of 4 minus. This one's nicer because if you plug in 1 into any logarithm, you get 0. So the whole thing just goes to 0. So that takes care of that one. Here I'm going to do minus 2/5 times 2/5 is 4 over 25. And then really I just got to focus on plugging into this right here. So I get minus. If you plug in a 4, again, I already said what that is. That's going to be 32. And then if you plug in a 1, 1 to any power is just going to be 1. So I'm cleaning this up a little bit more. You have 64 over 5 ln 4. And this is going to be minus 4 times 32 is 128. Let me do this a little nicer. This right here, that's 31, right? So then I'll do 4 times 31 is 124 over 25. And that's as far as I'm going to go for that. Okay, so let's review. We just had a u-sub, and then we had two possible integration by parts. I say possible because maybe someone came up with a different method. If you do, let me know in class. I would actually be very interested if you showed me that you did these first before me and got a same answer but with a different method. I'd love to see it. I'm going to get this stuff erased, and then we're going to do 3 more practice problems. So I'll see you soon. All right, welcome back. So here are 3 more problems. I feel like these are a little bit more difficult. I turned up the difficulty on these. So give these a try. Return to me when you're done. I'm going to get started. So I'm looking at this first one, and immediately I see like this radical right here. And we didn't really do any other technique besides trig substitution, where we had radicals. And this right here, this is not a sum or difference of squares. So before we even do our trig sub, we have to make it a sum or difference of squares. So we're going to complete the square. So let's go ahead and do that, and then we can use our method of trigonometric substitution. So off to the side here, I'm going to say x squared minus 4x, just like this. The a term is 1, so no factoring necessary. Half of the b term is negative 2, and if you square it, that's going to be 4. So I'm going to add 4, and I'm going to subtract 4 to this line. So 4 minus 4 gets us back to where we started again. And then once I've added b squared, or b over 2 squared, and subtracted it, I can factor this as x minus 2 squared, and this is minus 4. And now what I've done is I've completed the square. So this is what's going to get plugged into my integral. So this is going to be now going to be equal to, and I'll start writing it over here. This is dx. This is the integral of x minus 2 squared minus 4. And now I have to pick the appropriate substitution where I have a variable part minus the constant. And at this point, you should have these memorized. So the substitution for this is x minus 2 equals 2 secant theta. So the variable part minus a constant, that one, if you go back and look, that's secant. And if I take the derivative of both sides, that's dx is equal to 2 secant theta tangent theta d theta. And while I'm at it, I'm going to do some stuff for my triangle. So if you go up here, I'll just say x minus 2 divided by 2. That is secant, just solving this equation. And we know secant is, it's hypotenuse over adjacent. OK, and then while I'm at it, I kind of like doing it this way, now that I've done a bunch of these. I'm going to go ahead and draw that. So adjacent is 2. Hypotenuse is x minus 2. And that just means that this over here is going to be x minus 2 squared minus 2 squared is 4. But I know what that's equal to because I just wrote it right here. That's the same thing as this. This is x squared minus 4x. So I'm just going to rewrite it like that because I know that's what it's equal to. OK, so now let's make our substitution. Dx is the same thing as 2 secant theta tangent theta. X minus 2 is 2 secant. So then if I square that, I'm going to get 4 secant squared minus 4. And now from here, what I'm going to do is I'm going to say, well, secant squared minus 1, we know that is tangent squared. But this would be 4 tangent squared because I multiplied everything by 4. And then the square root of that would give me, I'd have 2 secant theta tangent theta d theta. And then square root of 4 is 2. And then tangent squared, I'm going to get tangent if I square root that. The tangents are gone and the 2's are gone. So this whole thing just simplifies to the integral of secant, which I know what that is. That is ln of secant plus tangent theta plus c. And then finally, I just need to plug in what those are. So that's ln of secant, I know what that is. It's x minus 2 over 2. Tangent is going to be opposite, which is square root of x squared minus 4x, over adjacent, which is 2. So that is the correct answer. I'm going to do something else, though. I'm going to take this opportunity to show you some little nuance to how you can write the answer to this. So then I'm going to keep going. I'm going to add these together because they have a common denominator. So I can put everything in the numerator over 2, just like that. But notice that's the exact same thing as having a 1/2 multiplied out front. So it's like I had 1/2 times this stuff in here. Does that make sense? OK. So who am I talking to? I don't know. So then if I have this times this, log rules say that if you have two things multiplied, you can split it up as addition. So this is equal to log of the first thing, 1/2, plus log of this more complicated second thing right here, plus c. However, log of 1/2 is a constant. So this plus the constant c is another constant. So let's just say this is log of x minus 2 plus square root of x squared minus 4x, and then plus d, some constant d, where it's these two combined. And what I noticed is I have these absolute value bars. I better keep these, because I need to make sure the thing in the log is strictly positive. So this will be my final answer, where I've taken this constant part out, and I rewrote it as another constant d. It's just a small, really technical thing that you could see, and it could come up, and it could confuse you. So I just wanted to clear that up now, that you could see it written like that. All right, let's take a look at this next one. So what did you think of this? My first thought was to immediately factor it. So for me, I rewrote this as x minus 2, x plus 1. And then I was like, oh, that's partial fraction decomposition, and it's the non-repeated case. So what I did off to the side is I started doing this. I said 1 over x minus 2, x plus 1 is sum a over x minus 2 plus sum b over x plus 1. And from here, because they're both linear and these are both the highest power of that factor, you can do cover-up method, which is always very nice when you can do that. So based on the cover-up method, if you plug in 2 and cover up the factor over here that is 2, you get 1 over 3 for a. And then similarly, if you plug in x equals negative 1 and cover up this factor, you get 1 over negative 3. So then what happens to this integral is you get the integral from 0 to 3, and it's going to be 1 over 3 times 1 over x minus 2, and then minus 1 over 3 times 1 over x plus 1. So that's all fine and dandy. However, there is a problem. So let me just write out a little more. So I have 1/3 integral from 0 to 3 of 1 over x minus 2 dx minus 1/3 integral from 0 to 3 of 1 over x plus 1 dx. The problem I'm referring to is actually right here. It's this first integral. We just talked about improper integrals. 2 is part of this interval. However, 2 makes the function go undefined. So actually, while this is a partial fraction decomposition problem, PFD, it is also an improper integral problem. So they're combined in this question. OK, well, the problem here is that at a equals 2, we're discontinuous. And that's that case where we're right in the middle, not in the middle, but we're strictly between the two endpoints. So we have to check 0 to 2, and we'd also have to check 2 to 3. So let's first look at the integral from 0 to 2. That's where the problem is. And we're just going to focus on this integral, 1 over x minus 2 dx. Who cares about the 1/3 right now? Let's just check what this is. Okay, so because this is not continuous at 2, I need to take the limit as t goes to 2 on the left. Integral from 0 to t of 1 over x minus 2 dx. And then here what I need to do is integrate this 1 over x, that's ln. So this is going to be the limit as t goes to 2 on the left, ln of absolute value of x minus 2. I need to evaluate that from t to 0. So that's the limit as t goes to 2 on the left. Plug in t, and I get t minus 2, absolute value. If you plug in 0, you get absolute value of negative 2, which is just ln of 2. No more absolute value needed, because 2 is a positive number now, and I've evaluated that as 2. OK, so what happens when I plug in 2, when I get very, very close to 2? Well, I'm going to draw that picture again that I've been drawing. As we get closer and closer to 2, this quantity gets closer and closer to 0. The absolute value bars will ensure that this is a positive number that is getting closer and closer to 0. So what's happening is I'm traveling down here. I'm getting closer and closer to 0 on the ln of t graph. However, as we get closer and closer to 0, this goes to negative infinity minus some constant. So this actually diverges. So even though it's nice that we know how to do the partial fraction decomposition, we could get the answer as ln of x minus 2 minus ln of x plus 1. Like, we could do that, but it won't make sense because for the bounds we have, there's a problem at x equals 2. So you could do all that work and then not even realize that we actually have a problem in the interval. So this diverges. However, it's a good exercise to be able to do the partial fraction decomp, because sometimes we'll just give you an indefinite integral. So this was a good review of 2 at once. So that was a good problem. All right, so let's give this last integral a try. The integral is from 0 to ln of 10. It's not 9. I'm hoping I gave a warning to you, because in certain parts of the video, that was 9. It doesn't change the integration process, but hopefully I warned you. It's from 0 to ln of 10 of this right here. So nothing else changed. Now, sometimes you're just going to come across really weird integrals, and you're not going to know exactly what to do at first. You can tell this isn't really integration by parts because there's 3 kind of distinct things happening here. There's no trig functions, so it's not a trig integral. There's no really completing the square idea here either, and this isn't factorable. So after all of those are exhausted, that kind of leads me to believe that we're going to have to do a rationalizing substitution. And at the very least, we're going to have to do some kind of substitution, because right now it just looks really bad. And the moral here is, if the first thing you try doesn't work, just try a couple other things. Don't get too frustrated. Not all of them have a clear path to the end. And in fact, if anyone figures out a different way to do this than how I did it, I would love to hear it, because I sat with this for a few minutes, couldn't quite figure out a good way, and then eventually I found a way. But I'd love to see what other people tried. So let me show you what I did try. So this is going to be u equals. And in my mind, u substitutions are great for complicated radicals. So you don't want this mess inside of a radical. It's very hard to integrate that. So I eventually decided to make u equal to the stuff in the radical and just kind of see what shakes loose. So then if you take the derivative of this, you get e to the x dx. And I was quite happy with that, because e to the x dx also appears here. So this is going to disappear as well, which is a bonus. Now, you have this factor in the denominator. And notice what I do here. So if you add 9 to u, we're going to do algebra 1. If you add 9 to the left side, the right side becomes e to the x plus 8. It's a very simple idea, but you wouldn't really think to do it unless you were trying to shoot for that, basically. So keep that in mind. You can do minor manipulations to the u equation if it helps you progress. All right, I'm going to take this. I'm going to substitute this in. So if you plug in 0 for x here, you're going to get 0 again for u. And if you plug in ln of 10, e to the ln of 10 is 10, minus 1 is 9. So there's the 9 that I accidentally put earlier in this video. I think I was thinking ahead. So here's 9. I've switched it into u's. E to the x dx, this right here, that's du. This is the square root of u in the numerator now, because I have that's u. And then right here, this is u plus 9. So while this integral looked a lot better, we still don't really have a technique to do this. I mean, I was thinking maybe you could do integration by parts, where one of the functions is 1 over this, and the other function is u to the 1/2 du, but I don't know. Like, it didn't seem good to me. They're both also algebraic, so how would I pick which one is u? And a lesser problem, but also annoying, is the variable is also u, so doing a u sub would be annoying. I'd have to pick a different letter. So what I did here, it's another rationalizing substitution. So this is another rationalizing substitution. So if at first you substitute and something doesn't work, you substitute again. So this time what I said is I'm like, OK, I'm really sick of this radical being here. So I just said, let w be u to the 1/2 power. Then this means dw is 1 over 2 u to the 1/2 power, so if I take the derivative. However, this is 1 over 2, and then u to the 1/2 power is w. So this is 2w. Oh, right, this is du, right? And this is du, because I take the derivative of this. And then if I solve this one, this tells me that 2w is actually equal to, 2w dw. I'm going to multiply the 2w over here. So 2w dw is du. And then what about this? So if w is u to the 1/2, if you square both sides, w squared is equal to u. So all of this came from the fact that I started by saying, OK, I'm going to substitute out the u to the 1/2, and I got all these different things that I needed. We are now going from the u variable to the w variable. So if you plug in 0 into u, you get 0 for w. If you plug in 9 into u here, 9 to the 1/2 power is 3. U to the 1/2 is w. du is 2w dw. And then u plus 9 is going to be w squared plus 9, because u is w squared. So this is the integral from 0 to 3, 2w squared over w squared plus 9. This is a polynomial divided by a polynomial, and this is not proper. The degree of these match, and you need the degree of the numerator to be less. So I did long division. So I'm going to divide this one into 2w squared. And this goes into this 2 times. And then multiplying across, I get 2w squared plus 18, and I subtract that. So I get minus 18. That's my remainder. So then this integral here turns into the integral from 0 to 3. I get 2, and then minus 18 over w squared plus 9. Now the integral of 2 is easy. That's just a constant. So we get 2w, and I'm going to evaluate that from 0 to 3. Minus, here's a constant, 18, integral of 1 over w squared plus 9. And this is from 0 to 3 as well. If you plug in 3 and you plug in 0, you're just going to get 6 for this first part. This is minus 18. And then what better way to finish the whole review video is to review this rule. So what is this integral? I have 1 over a variable squared plus a squared. That's arctangent. So this is 1 over 3 is the constant getting squared. And this is arctangent of w over, and then it's 3. And this is evaluated from 3 to 0. So this is 6 minus 1/3 of 18 is 6. and I have arctangent of 3 over 3, which is 1, minus arctangent of 0 over 3, which is 0. So this is 6 minus 6 times arctangent of 1, that's pi over 4. That's the angle that gives you 1 for tangent. And 0 is the angle for tangent that gives you 0. And then this will be 6 minus 6 over 4 is 3 over 2, and then pi. So we got there. This was just a very unorthodox kind of problem. This one was just to challenge you, to let you sit down and think and just try some things. Even if the first thing doesn't work, just try something else. This is what worked for me. I did 2 substitutions. Something else could work better. I don't know. But I just wanted to show you what I was thinking. All right, we've reached the end of our review. It definitely does not stop here. You should go find review sections in calculus textbooks that mix all the integration techniques and go try them. You should really push yourself to try problems where you don't know ahead of time what technique you're supposed to use, and then find the best one to use. All right, send me any questions you have, and until next time, I'll see you. Bye.